Okay, so the two talks. The first talk is we're going to discuss the vacuum wave function in the geometric representation of Clifford algebra, where Clifford algebra is the math language of quantum mechanics. It's normally we see it in the matrix representation of Pauli and Dirac. Uh, then we'll look at the wave function interactions with the geometric product, and they generate something one can call a geometric S matrix. From there, we have to physically manifest this thing, which we can do with a coupling constant, and we have electromagnetic quantization and an electromagnetic scattering matrix. So, working in the geometric algebra and extending the Dirac spinor to the full vacuum wave function. The claim is that it's a universal language for mathematical physics. That was Clifford's intent. The paper was published in 1878, and he died in 1879. So there was not a strong advocate to oppose Heaviside and Gibbs, and when the math war was happening, basically between quaternions and vector algebra, which is true in 3D only. So without the geometric algebra, Einstein adopted curved space, the Riemannian approach of curved space, and in the geometric picture, spatial curvature is equal to quantum phase. It's a phase shift. And likewise, Dirac, he ended up in the unintuitive matrix representation because he didn't have the geometric. It was rediscovered by Hestinus and the Cambridge group from 1965 onwards and extended quite a bit. So what this is about is division algebras. We want algebras in which we can divide. It's essential for singularities, topology, dark matter, T-duality of string theory. There's 4 normed division algebras. The norming means that you have a zero in it, and you can put that some specific place, and that you can scale it in the presence of that zero. So there's only 4 algebras you can do that. The real is 1 dimension. The complex, 2 dimensions or degrees of freedom. The quaternion 4 and the octonion 8. And something called the Hurwitz theorem proves this is true. So they're Clifford algebras, Pauli matrices are basis vectors in 3D space and Dirac in 4D space-time. So it's a nice simple model. It's something you can visualize. You've got these geometric objects, and they're in the basis of 3D space or 4D space-time in the natural language. And that vacuum wave function is the same at all scales. So Hestinus, when he published the second edition that you can download for free here, when he published this, all he did was add a preface, and in the preface, he dwelled upon this "be bold and explicit in making claims" view, which I think is certainly because in the 50 years since he published the first version, the geometric algebra is still outside the mainstream. It's been adopted so slowly. So here's some bold and explicit claims that the models naturally gauge invariant, finite, without renormalization, confined, asymptotically free, background independent, contains the 4 forces. I was going to do more in the abstract, but if you do too many extreme claims, people start to think you're a crackpot. But it actually has a nice explanation for unstable particle lifetimes beyond standard model explanation. You can do branching ratio calculations. It has dark matter, dark energy, a nice model of the Big Bang, and inflation, quantum interpretations. Quantum interpretations is important. It starts with the wave function. You're not solving for a wave function in a differential equation with an Lagrangian. You're starting with the wave function and going up from there. So that's a really important aspect of this. So the theoretical minimum is 3 assumptions. You start with the geometry, point, line, plane, and volume elements. That's geometric quantization. You get a vacuum wave function, a scalar, 3 vectors for the 3 orientational degrees of freedom, 3 bivectors for the area elements, and 1 trivector. So then you have electromagnetic quantization with the fine structure constant. These four fundamental constants that define alpha let you assign appropriate flux quanta to the 8 wave function components. And you need a metric. So the mass gap, the lightest rest mass charged particle, the electron or the photon electron interaction that's the foundation of QED, is the metric. And then you can have positrons and electrons interacting with each other and via the geometric Clifford product, which changes dimensionality. The algebra thing is funny. If you start with two vectors, two lines, and multiply them together, what comes out is a scalar and an area element. So to this complicates the model a bit because it's nice. You started out with this vacuum wave function. You gave it electromagnetic fields, but now you have to have this energy moving around between different dimensions. So the algebra is a bit subtle. It has no free parameters. So the phenomenon of emergence, that the rest of what you're going to see emerges from these three assumptions in terms of the model that's being presented. So we're going to look at the algebra in more detail, look at interactions, the geometric product, and the geometric scattering matrix. The claim that was made early on was that geometric algebra is the universal language for mathematical physics. Hestinus did a nice job of just putting all of this together in a visual for us. And he was awarded the 2002 Oersted Medal by the American Physical Society for reforming the mathematical language of physics, which is basically what he's done here. So when we look at the algebra itself, if for instance we want to take the product of two vectors, if we say we've got a two vector bosons W and Z, so this product changes the grades. The scalar product lowers the dimensionality of the vectors, so you end up with a scalar. And the wedge product raises the dimensionality, so you end up with a bivector. The bivectors are spin 1/2. So this is WZ equals Higgs plus top. If taken together, these four super heavies are a minimally complete 2D algebra, a scalar, two vectors, and a bivectors. The sum mode of the W and the Z is the top within 1%. The difference mode is bottomonium, the dominant decay mode of the super heavies, and so there's no Higgs here, which is curious to me, but I don't know if it's actually meaningful. So this is what the geometric S matrix looks like. You've got the electric charge, you've got the scalar. So these are the flavor SU3 matrices, and this is the color SU3 matrix, and this stuff is SU2, and that's U1. And this thing over here, this 6-dimensional thing, there's once you get into, so the extra dimensions, the way this works is there's just three space dimensions, but the extra dimensions are time emerging. And when you have 3 dimensions, you need 3 quantum phases. So the extra 3 dimensions are phase. Time is the integral of phase, and it's the same for all 3 orientations, but phases are different for the 3 orientations, how energies pass back and forth with Maxwell's equations. So we put the physical manifestation in, and we look at the electromagnetic. So how we get the physical, we start with this here, these four constants, and electric charge we're given right away. Magnetic charge we get from the Dirac relation. Magnetic flux quantum is a fundamental constant, and interestingly enough, this is a trivector, a volume element, and this is a vector, a line element. So there's a topological thing going on here that'll come back to us when we're looking at neutrinos. The rest of these I'm not going to go into in detail, but this is how you do it, and the notation's horrible here. This is something I did back in 2011 and haven't cleaned up, but it works. It seems to be mathematically correct. So this is what the Dirac wave function looks like. You've got a charge and a magnetic moment, and these are the modes of the Dirac wave function. Most of the mass is right here at the Compton wavelength. This is the heavy stuff, the electron exciting the positron, and the coupling of that mode contains a lot of energy. And this much less so. This is you have to go down to a factor of alpha smaller than the Compton wavelength for the electric charge to energy to equal the rest mass. Here we want to see just the connection between the unstable particle lifetimes. The horizontal axis here is the speed of light multiplied by the lifetime. So it's the coherence lengths. And the coherence lengths, when you plot the impedance network of this of the these colored symbols here are various modes who have their impedances plotted in the next figure. When you make these plots, you see naturally the impedance networks, what governs the flow of energy, the amplitude and phase of flow of energy. These impedance networks are structured in powers of the fine structure constant, which makes sense because that's how they were defined. And they coincide with the coherence lengths because you have to have impedances matched for energy to flow, and that happens at the impedance nodes. So this is an explanation for unstable particle lifetimes that you won't find, I think, anywhere else. There's occasionally objections that how do you deal with special relativity in this? And it's important to keep in mind all of these modes of the scattering matrix are two-body, and special relativity, the Lorentz transform is Pythagorean theorem. It's three-body. It's emergent. The first place you see it in this model is the neutrino, the three-component neutrino. So the origin of inertial mass, where am I? I'm still here. The origin of inertial mass. Just briefly, you can understand the origin of inertial mass in terms of the energies of these various modes. So these, I'm not going to go into detail too much more, but you can see most of the modes that you get with the fundamental constants, the possible modes, are at one of these three places, either at the Compton wavelength or the Bohr radius or the classical radius. The difference here between the 14.9 keV and the 3.7 keV, there's factors of 2 floating around that just I don't know how to deal with, but this is 3.7 keV is 14.9 divided by 2 squared. But then again, it's only really one factor of 2 because this should say 1.02, twice the rest mass. Okay, I'm done with this. Thank you very much for listening.
Okay, thank you. You're on time. I was wondering, you said something about there's not being a Higgs. I mean, how does a Higgs fit in? That's the origin of inertial mass in the standard model.
Oh, good. Thank you. Right. So the Higgs, so what happens here now, you've got two magnetic charges. These guys are spin 1. That's what the trivector is. And the product of these two magnetic charges gives you a spin 2 thing that's got 6 degrees of freedom, 3 of space and 3 of phase, and a spin 0 scalar. So this in the model appears to be the graviton, and this appears to be the Higgs. The Higgs is the scalar, but it's not this scalar. It's a different scalar than the electric charge scalar. And the sexta vector is the graviton, which would make sense that the two of them are entangled, that the origin of mass and the communication of gravity are somehow connected in the same mode.
Can you get the standard Yukawa couplings of the Higgs to fermions?
I don't know what a Yukawa coupling is.
That's a standard model interaction between the Higgs and fermions. It's been measured quite precisely.
I haven't. So I come from such a different direction from
I understand.
Yeah, but that's certainly an interesting thing. And I'm going to try to remember to look at Yukawa coupling. Thank you, because to get that would be very cool.
Yeah. Okay. Are there any other questions? Are we ready to go to the next talk? Okay, Peter, go to the next one.
Okay, we're on our way.